alguien está respirando en el micrófono.
We almost start. We're waiting for the streaming on Facebook Live to be ready.
So is this any project that it's a collaboration or?
Yes, it is a collaboration. So I'm working with, okay, I can go ahead, with Moritz. He's a master student in Munich here, and Hans-Peter Nilles, he's in Bonn. Saul, you probably all know.
Oh, okay. Yeah, now I see the connection.
He is also in Munich.
Yeah.
Yeah.
Saul is the link.
Is Saul still in Germany, or is he back to Mexico?
He's already back.
Oh, okay.
2 months ago, so he came back. Yeah.
Okay, so we're now live on Facebook. So let me introduce you. So today, thank you for everyone to attend to today's talk. Today we have a guest from Germany. He is Alexander Baur. He is a student at the Technische Universität of Munich, where he works with Patrick Baudrevanche, I think. And he is also a PhD student at UNAM, where he works with Saul Ramos. He's going to talk about the flavor symmetries and how can they arise from string theory when compactified in orbifolds. So thank you, Alex, for accepting our invitation to participate in this seminar. So, well, you may begin, please.
Okay, thank you, Miguel. Thank you for the introduction, and of course, thank you for having me in your seminar. Today I'm going to be talking in English. So I'm going to be talking about flavor from strings on orbifolds. And yes, this is work based on, or this is based on work with Moritz. He's a master student in Munich, or he was a master student, with Hans-Peter Nilles, with Saul, who you probably all know, and with Patrick Baudrevanche. Okay, so my motivation is as follows. I want to start with something you all know, and this might be the standard model of particle physics, hopefully. And so you probably all know this picture, and you all know the gauge group SU3, SU2, U1, which somehow acts in this region, and of course the color region, which I haven't depicted. But all of you also know that there are 3 flavors or generations of standard model particles, like 1, 2, 3. And that the standard model has masses, which are free parameters, so you have to determine them by experiment. Masses for quarks, masses for leptons, and since newest, masses for neutrinos. And those masses even have mixings, which gives you another, for the CKM or for the PMS, free parameters which you have to measure by experiment, or which they are not. So there's no motivation or origin from a theory point of view. And I want to more or less fix this, or shed a light on why we have 3 generations. And this, so a possible explanation might be by a flavor symmetry, which acts like in this direction of the standard model. Okay, so the outline of my talk is I want to more or less go from top down to bottom up. So I want to start with some string theory basics. We're going to then talk about extra dimensions. Before we're going to see how the flavor symmetries come from these extra dimensions. So orbifolds are extra dimensions. And yes, we're going to then take a look at eclectic flavor symmetries, which are somehow in between the bottom up and the top down approach already. And then, since we haven't reached all the way down to the parameters, to predicting the parameters from the top-down point of view, I will then come from the other side and explain to you something about modular flavor symmetries and why we are going to use, or why these flavor symmetries that come from orbifolds are that interesting. Okay, so first of all, usually you get to ask, is string theory useful to describe nature? And of course, honestly, I don't know. So, so you might ask, why do we do it? And then, so there's a lot of reasons. So it is a theory of quantum gravity for starters. It provides a possible UV completion of the standard model. And some others say it is fun, which is of course legit. So all these reasons, and there are way more reasons, I think they say that string theory deserves to be studied. Okay, so let us start with some basics about string theory. And so the most basic idea of string theory is that the fundamental objects are not anymore point particles, but one-dimensional objects, so strings. And if you take a one-dimensional object, I mean, there are two possible topologies for one-dimensional objects. This is either this or that. And of course, this one we will call an open string because the endpoints it's open. And this one is a closed string, so start and end point are at the same point. It is a closed string. Okay, today we're going to take a look at closed strings. So how do we describe a string? So we get a coordinate for this string. So the coordinate describes where in our not four-dimensional space-time, but whatever our target space-time is, where the string is. This is the coordinate of the string. And you see here two dependencies. One dependence is for where on the string you are. And the second dependence is more or less the eigentime of the string. So if you take a string over here, this is in space, so you have a string in space and it propagates through time, you will somehow sweep out the so-called world sheet. This is why we have two coordinates over here. Of course, you can go on and try to find equations of motions for your strings. You will find this nice equation, which looks pretty similar to a wave equation. And the solutions to these equations is pretty unique to string theory because you can divide the solution in two parts. One which depends on tau plus sigma and one which depends on tau minus sigma. So one which we call it L because it moves in the left way, and the other one we call it right because we call them somehow right movers. This is what this picture here says. So imagine you have a string and you have this sort of wave equation for the equation of motion, so you can have oscillations inside your strings. And now if you have a string and not a point particle, you can have these oscillations, and these oscillations can move either the left way around the string or the right way around the string. And this is the left and the right mover of the string. And the last thing for the basic string theory is the boundary conditions for closed strings, because we're going to need them later on. So if our string is closed, that means if we take this sigma variable, which was the one which moves here along the string, and go, and we're back at this point, which is about exactly 2 pi later, and we will be at the same point, so this coordinate has to be the same. And this is why we call this a boundary condition for the closed string. Okay, if you have questions, comments, or anything, please interrupt me right through the talk. I'll be happy to talk with you. Okay, so the thing with string theory was the most, the most weird thing is that it is anomaly-free only in 10 dimensions or 26 dimensions. So anomaly-free according to the Weil anomaly. You can also try to quantize this theory and see that it will give you negative norm states or there's no Lorentz invariance. Take the reason you want, you will always end up with 10 dimensions. So string theory somehow needs to be in 10 dimensions, or otherwise said, the oscillators need to be able to move into 10 dimensions, or need a 10-dimensional space-time to move in all directions. Or 26, of course, if you only do bosonic string theory. And this is somehow weird because if you look around you, you will probably see 3 to 4 space-time dimensions. Depends if you consider time a dimension or not. And now I tell you it is 10, so there is somehow a clash. And therefore we need to, we call it compactify, or even roll up those extra dimensions, make them really small. Aside, maybe to understand this very vividly, consider this picture. So we have an electrical tube and we put some voltage from the right and on the left side. And so we got a metal tube, so there are some electrons in it. And if you now take this tube and tube and move it really, really far away, you will probably see that electrons move from the left to the right, nothing else, because it's so far away you don't even see that it's a tube. You'll see it as a wire. But if you take a really, really close look at it, you can see that the electrons could not only move in this direction, or can not only move in this direction, but could actually move here around. And this is the same thing with the extra dimensions. So if we take a close look, we see the tube. If we take a really, really far look, if we don't look at it that closely, or with not that high amount of energy, we will only see a wire. So we will only see one dimension. Okay, so in this somehow picture, we more or less rolled up one extra dimension. So we have one extra dimension here. And of course, for the extra dimension to not see it, it has to be really, really small. This is just a rough number to give you an imagination of how small it should be, like really approximately really enough number. But this is only one extra dimension. Of course, we can add another extra dimension. So we add another circle, which means that on this second circle, of course, on every point, there is this other circle, which somehow looks like this. Or if we even go further, it will be a torus. So a torus comes out if we roll up two extra dimensions. Now, you still look around, you see 4 dimensions, you say 4 plus 2 is 6 and not 10. What the hell is he telling me? Let's just take 3 of those tori, and then we have 4 plus 6, and this is 10, and we're happy. Of course, the torus is really, really simple. There are more elaborate ways to compactify, like, for example, Calabi-Yau manifolds. I think Joaquin told you about them a lot. For example, Joaquin. And but to be honest, they look really, really complicated. So let's go back to the tori. And even 3 of them are quite difficult. So let's just take one and treat it as like a toy example. Of course, one torus, as you might have guessed, is too simple, and it will lead you into problems with supersymmetry, which is why we can do a more elaborate step and take this torus and divide it by 3. Or mathematically speaking, we mod out the Z3, so an abelian group of order 3. And we then get this funny object over here. And this is what we would call an orbifold. So this orbifold, we can also fold it up. So if we take this line here and fold the orbifold up, we get this nice picture over here. And we see that this orbifold has 3 singularities. So the spacetime has singularities x, y, and z. And those will become interesting. Okay, so next thing you might ask is, how do strings live on these objects, on these orbifolds? How do strings propagate in those extra dimensions? What kind of strings are there? And there are, well, several kinds of strings. The first ones are the trivial strings. Why do I call them trivial? Because they do not wind, they just lie on here. They do not wind around a singularity. And they therefore fulfill this usual boundary condition that you remember from 1 or 2 slides before. But if you are on a torus, you can imagine that if you go 1 time around the torus, you end up at the same point. So there might be another way to close the string, and those are called winded strings, because you wind 1 time around the string. So if you move along the string, you will end at the same string, but you wind it 1 time around it. And this is why we call this end of winding number. Of course, this number is highly restricted. It can only be 1 torus surrounding. But those winded strings, well, they are kind of, or mostly, or in general, massive. And massive means massive at the Planck scale. So they're really, really heavy. We won't see them at the LHC or anything in near future. However, there is a third kind of strings, namely the twisted strings. Why do we call them twisted? Because they like twist 1 time around. Or you remember we divided the Z3. So just imagine you go on, or really roughly imagine you only go 1/3 of the torus. But since we divided out the 3, you will be at the same point. This is what these theta here means. So the theta is for the Z3. And of course, you can also wind around the string. So those twisted strings, they're localized, or their center of mass is localized at those singularities here, x, y, and z. And those strings can, in principle, be massless. So massless from a string theory point of view. So they don't have Planck scale. They're really, really massless. So we can actually might be able to see them. Okay, so these are the three strings. We're of course interested in the twisted strings because they are massless. Now, next thing might be flavor. And you might ask me, okay, now we know those orbifolds. You promised us flavor symmetries. And therefore, I want to make an analogy. So, in our four-dimensional world, you know, the symmetries of our, say, Minkowski spacetime or whatever you want, is the proper Poincare group. So it represents the symmetries of our spacetime. And, well, the representations of this, let's say, proper Poincare group, or the Poincare group in general, build up our fundamental particle states, spinors or something like that. And there are these three transformations, like C, charge conjugation, P parity, T, time reversal. And these transformations interchange these representations. You know, like a left-handed or right-handed particle, they can get interchanged by, for example, parity transformation. And of course, also the conjugacy classes. You might ask why, or is there more behind that? And that is because the C, P, and the T transformation are symmetries of the proper Poincare group, or mathematically speaking, they're automorphisms of the proper Poincare group. Okay, this is for the 4D world. And somehow roughly the same thing happens in the extra dimensions. So if we have extra dimensions, we would also have some sort of symmetry group that describes the space-time symmetry of our extra dimensions. And this symmetry group also has, again, symmetries or automorphisms like the CP and T. So we will have CP and T transformations, but not for the four-dimensional world, but for the extra dimensions. And those will give rise to the flavor symmetry. So what we're going to do, if you want to get the flavor symmetry, we will take our extra dimensions, take a look at them, describe the symmetries of the extra dimensional space-time by a group, like the Poincare group, but only for the extra dimensions. So let's call it the space group. And we will then calculate the automorphisms of this group. And because, well, our particles correspond to the representations or conjugacy classes of the Narayan space group, so of the Poincare group of the extra dimensions. And therefore, the automorphisms of this Narayan space group, they will somehow interchange our particles. And this is what we want for a flavor symmetry, right? We want to exchange an electron to a muon or a tau or whatever. So we describe the extra dimensions by the Narayan space group. We calculate the automorphisms of the Narayan space group, and we then see or check how the strings behave under those automorphisms. And this will then be our flavor symmetry. Okay. Now this is a lot of matrix multiplication. Yeah, you have a question.
Sorry. Yes. Maybe I'm getting a bit ahead, but if there is some sort of condition over the extra dimensional space group that guarantees that you are going to find some interesting, phenomenologically speaking, automorphism of this group.
Mm-hmm. Yes, so okay. Well, so what you can do is you take a look at all the possible extra dimensions that there are and take a look at the automorphisms and therefore take a look at all the flavor symmetries that can come out. This is what Jesenia and Ricardo did with Soul, for example, the MSSM-like particles.
Okay, but there is not like a mathematical statement about, like, say, these extra dimensional space groups are always going to give you nice automorphisms or so.
No, not that I know, no. But it would be interesting, yeah, if there is maybe a really mathematical general way.
Yeah,
to
okay,
look at.
so
Right.
everything is like a numerical calculations, and you try and maybe it works, maybe it doesn't, and so on, right?
It is like that, yeah. Yeah. And of course there are like, I don't know, thousands, or I think we even know finite ways to have extra dimensions. So yeah. So an automated way would even be nice, but of course a general mathematical way would be the holy grail, I guess.
Yeah,
But
maybe it's a little bit ambitious, but at least to get like a bit a small classification, you know, like by parts. Maybe, yeah. Okay, thank you, Alex.
Yeah, maybe an automated way can help you with a small classification, maybe to start with.
Yeah.
Okay. So I don't want to take you through how I actually calculate, because it's matrix multiplications and so on and so on. It's quite boring, I figured. So let's go straight to the results. So for this funny object that I presented you already, it's the T2Z3 orbifold, we call it. We find this sort of flavor symmetry, and this group is called delta 54. It has 54 elements. That's what 54 stands for. And so we call this a traditional flavor symmetry because this delta 54 is more or less nothing new. How can we explain this delta 54? So you remember our orbifold had 3 singularities, and there are more or less three automorphisms that generate the delta 54. The first two are really simple to see. So we can, of course, interchange those two singularities, or the strings that live at the singularities. So remember, the twisted strings are localized at the singularities. So we can interchange the strings that live at y and z. We can, of course, here change in the circle around so the string of the x gets to the y to the z, and the z to the x. And we can combine those two. It will give us an S3. We call it geometrical symmetry. And the other way is a purely stringy way. So we can add faces to the x, y, and the z to the strings, and combine those two, and these will give then us the so-called string selection rules, Z3 times Z3. So this is a purely geometrical way that had nothing to do with string theory, and this one is a purely stringy thing. Okay, so in our case, the actual automorphism of the space-time symmetry would, in this case, be a 180-degree rotation. In this one, it's a translation in the winding number, and the third one would be a translation in the Kaluza-Klein number. Good, and well, those two together, they generate the delta 54. And this is then the flavor symmetry. So as I just said, Cecilia, Ricardo, and Saul, they looked at the MSSM-like orbifold models, so the orbifolds that give you MSSM-like models, and classified actually all of the traditional flavor symmetries that can come out of there, which is I guess quite impressive work. And I imagine that it has been a lot of work to do that. And yeah, also at the UNAM here in Mexico, they also did a pheno with a delta 54 flavor from orbifolds, and saw that they are not too bad in terms of flavor, and in terms of being a flavor symmetry. Okay. So this was the traditional flavor symmetry, but we do even find more automorphisms. And those are, so we find this an A4 group, and we find a Z2 group additional to this delta 54. And this was like not found before, so we were really wondering, what is that? But if you think of it for some time, you come up that it's pretty clear what they are. So our orbifolds are based on a torus, and we divided this torus by 3. So the thing with the torus is you have to parameterize your torus, and you do this by a so-called modulus. So this modulus is the one circle divided by the other circle in complex numbers. And then you have parameterized your torus. But the thing is, if you take the same torus and you can parameterize the same torus differently, and you will then get a different modulus, but the torus is actually the same. So you have different parameterizations for the same torus, and this already smells like symmetry. So all the different parameterizations that give us the same torus, they are connected together by an SL2Z transformations. And therefore we call these transformations modular symmetry. So the modular symmetry is somehow the parameterization symmetry for the same torus, the one on the same torus. Okay, now our orbifolds were based on tori. We just divided out of 3. So we might expect that there is something similar happening for our orbifolds. And so the thing is, we won't see the full SL2Z, but we will see a subgroup of it or a quotient group of it. And this is the A4, for example, in this case. And the Z2 is also there. It also comes from the SL2Z. Okay, so we now know the flavor symmetries from this orbifold. They divide into 2 parts, the traditional and the modular part. And they have a traditional flavor symmetry and modular flavor symmetry. Good. Of course, we took this torus and we divided it by 3. There are, of course, other numbers you can divide by, or other things you can do to the torus to get an orbifold. And the next thing to do would be to divide by 2. So you get the T2 over Z2 orbifold. You won't get this funny 3-sided pillow thing. You will get this 4-sided pillow thing, or raviolo, as you might like to call it, or this pyramid, or something in between this shape. So the shape is not fully fixed in this T2 over Z2 orbifold. In the T2 over Z3 orbifold, the shape is fully fixed. In the T2 over Z2 orbifold, the shape is not fully fixed. Okay, you do exactly the same thing. You find the Narayan space group, you find the Narayan space group, you calculate the orthomorphisms of this Narayan space group, you apply these to your string states. So the same procedure. And you will get a traditional flavor symmetry, which is now dA times dA divided by Z2. And you also get a modular symmetry. You get an S3 times S3. So the Z2 is more or less the same. The one S3 is now the part that was the A4 before. And the first S3 here, this one corresponds to the possible shapes of the orbifolds. Okay, and of course there are 40 more ways to divide a 2-dimensional torus. And as you can imagine, if you want to divide a 6-dimensional torus, there is a huge amount of possible ways to divide this. So classification is really a lot of work. Okay, but we started with those 2, and yeah, let's see where it leads us. Okay. Very interesting for phenomenological parts are the representations that those groups have. For example, a delta 54 has 3-dimensional representations, and this is what we want, because we need in our standard model 3-dimensional representations. We need the electron muon tau. We need the 3 generations. This is why we want 3-dimensional representations for our flavor groups. And so for the delta 54, we have those 3-dimensional representations. For the modular group, we find at least 2 plus 1-dimensional representations, which is also fine, of course, if we want to describe 3 generations. Here we find a 4-dimensional representation, which is not that good. Maybe there's a 4th generation model, or we just need to consider a subgroup of our traditional flavor symmetry, because for some reason one of these fixed points is, I don't know, heavy or whatever. And yeah, here we have a 2 plus 1 plus 1-dimensional representation. Good. So you see, we have the traditional and the modular flavor symmetry, and they somehow combine. So you might, we have the traditional and the modular flavor symmetry, and they of course combine to the eclectic, so-called eclectic flavor symmetry. So the combination of both of them is the eclectic flavor symmetry. Now the interesting part is, so from the standard model, you know you have an SU3 cross SU2. and cross U1. So there's always a cross. It's a direct product. They don't interact with each other. They have nothing to do with each other. But the traditional and the modular flavor symmetry, they're not orthogonal to another. It's not a direct product between both of them. And this is what makes them interesting and very restrictive. So I put a union in between because we observed that sometimes the same object can be in the modular and in the traditional flavor symmetry group. So there are some strange things going on still. Anyway, what always has to be the case is that the traditional flavor group has to be a normal subgroup of the eclectic flavor group. So this is restrictive. The modular flavor group on the other side can only consist of outer automorphisms of the traditional flavor group. So you see again automorphisms. So automorphisms appear quite often in group theory. These are different automorphisms, of course. So this time they are the automorphisms of the traditional flavor group. And yeah, so this is a quite restrictive way. And they can only be a finite amount of eclectic flavor symmetries. If we only have a finite amount of modular symmetries or traditional flavor symmetries. By now we only know a little amount of modular symmetries, but I think it's the number of possible modular symmetries is growing. So the number of possible eclectic flavor symmetries might be growing as well. Okay, flavor symmetries of course always have to be broken. So this one will be broken by flavons, and this one will be broken by the VEF of the modulus. Good. I think I'm fast. Yeah.
Alex.
Yeah.
Okay. It seems like you broke your eclectic group like by parts, right? Like first you broke the traditional one and then you broke the modular. Is there any impact on the phenomenological results if you break first the traditional group and then the modular one and vice versa?
I don't think so, no. Of course, there are 1,000 ways to break. So there are different VEFs you can give to the flavons to break, and of course different VEFs to the modulus you can give. So the VEF of the flavon always has, or they somehow always is restricted to an energy scale, like where you can see the flavon and where you can't see the flavon, like with the Higgs process. How is it in the modular case? I guess you will also break it at a very high energy level for the modulus, because the extra dimension is really, really small, so it has to be at somehow high energy. Coming back to your questions, I think it hasn't been studied by now, the different breaking processes of both of them and how they affect phenomenology. So in fact, the eclectic flavor symmetries haven't been studied from they have been derived from a bottom-up point of view, but there hasn't been trying to do any real phenomenology. So they haven't been trying to match experiment, predict any neutrino masses or stuff like that. So I guess there's still a lot of research in the future, or possible research areas, let's say like this.
Okay. And I know that I always ask this, but the moduli only contains geometric information, right? Geometrical information, or does it have any field contribution?
It's different, like in the Calabi-Yaos, yeah. Let me see. I have this one slide about the moduli. So there are two moduli for a stringy torus. Like a usual torus always has this complex structure modulus, which you saw with one with the parametrization. And the second purely stringy modulus is the Kähler modulus. So you have the background field, the Kahl-Plummer background field, and you have the determinant of the metric, which is more or less the radius of your extra dimension. And these are the two moduli. So the moduli won't be won't be matter content or anything like this.
Okay, so if it has a physical field contribution, you can like establish a hierarchy between the BEV of the moduli and the flavons, right?
You should be able to, yeah.
Like for saying, like for made, I don't know how to say it. This arguments that goes like it is more natural for the flavons to be lighter or heavier than the moduli or so.
Ah, yeah, the naturalness argument.
Yeah.
It's always a difficult thing. Yeah, of course, I don't know what to say. What is natural? Of course, it would be nice if the flavon has a really low energy breaking scale, so we can see it probably soon. That would be nice, of course. But there are also flavons that. So what people also consider is flavons living in the bulk of the extra dimensions. And then, of course, the energy scale will be really high. So you'd have to see the extra dimensions to be able to see the flavons.
Okay.
Breaking scale.
Okay, so there is no argument for saying which part of the eclectic symmetry should break first.
No, not to my knowledge, no.
Okay, thank you, Alex.
Yeah. Where was I? There was I. Okay. Good. Since you're already asking a lot about Pheno, it's a good thing that we're coming now to the bottom-up part. So this is as far as we went from the top-down point of view, how far we got by now. And now I want to show you from a more bottom-up perspective. So what bottom-up people are doing and why we are that much interested in the modular symmetries, because they can do really cool stuff with those modular symmetries. And this is what I want to explain to you right now. So you remember that you could parameterize a torus in different ways, and so they're always parameterized by this modulus, and the moduli are connected by those transformations with a tau plus b divided by c tau plus d. So these were the SL2Z, the modular group, the SL2Z transformations. You can generate those transformations here by the so-called S and the T transformation. Maybe you heard of them before. So the S transformation takes tau to -1 over tau. So you take B1, C -1, and D0, A0. Or T goes to tau goes to tau plus 1, for example. It's rho, I'm saying tau, but it's rho. Rho goes to rho plus 1. And these two, they generate the full SL2Z. So they generate the full modular group. The thing is, so the modular group also has congruent subgroups. Like, for example, you can take any matrix ABCD, integer valued and determinant 1. So you take any matrix ABCD and you only keep the ones that give you the unit matrix, so the identity matrix modulo n. So you take the matrix modulo n and you get the identity matrix. This would be the congruent subgroup, for example. We name them like this. And the thing is, if we now take the quotient of those two groups, so if you take the full modular group and we divide by the congruent subgroup, we get this finite group. We call it finite modular group. And this finite modular group will be then the finite modular flavor group. So when we say A4 or F3 as a finite modular group, we mean these gamma prime 3 n. So for example, if n is equal to 2, we get an S3, or if n is equal to 3, the gamma prime n3 is equal to a T prime, for example. T prime is the lower cover of A4. Okay, now that you know what modular symmetries are, let's go to, let's dive into the real part. So say we have a theory that we call modular invariant. So it is invariant under the modular symmetry. And of course, this theory has a usual standard model Lagrangian, and it has Yukawa terms. And those Yukawa terms they have a Yukawa coupling here in front, and they have some fields, let's say n fields, just to be general. And yes, so these Yukawa couplings y and the fields phi, they are, and this is now important, they are first of all modular forms, or at least the Yukawas are modular forms. The fields only transform similar to the modular forms. And secondly, they transform with a rho I, so they transform as a representation of the modular group, of the finite modular flavor group, which means if we take this Yukawa coupling and we transform it, so we do this modular flavor transformation, we get, first of all, this orthomorphic factor here. This is how modular forms transform. And we get, secondly, this representation here of the finite modular group. So this is new to these modular flavor symmetries, because for usual flavor symmetries, you would say that Yukawas are just constant, they're just numbers. But here for the modular flavor symmetries, the Yukawas are not anymore just numbers, but they are modular forms. So they depend on the modulus, and they are modular forms, which is quite restrictive. Okay, and the fields, they transform in a very similar way. They also get this sort of orthomorphic factor, and they also get this representation. And this is also what we, for example, find in string theory, that fields transform with this orthomorphic factor, and of course get this representation. This is nothing new for a flavor symmetry. Good, which now means if we take our Yukawa term from the Lagrangian and we transform it with the modular flavor symmetry, we get this huge orthomorphic factor, which is now the chi y from here, and all the k's, all the modular weights, we call them, all the modular weights from the fields. And we get all those representations here, tensor product to one another, and of course our usual term. And we want this, of course, so we want the Yukawa to be, so the Lagrangian to be a variant under the modular flavor symmetry, which somehow means that this has to be 1 and this has to be somehow 1, or trivial to the identity matrix, which gives us that this one has to be a trivial representation. So the tensor product has to give us a trivial 1. And all those k's, they have to sum up to the ky, such that we have here to the power of 0 and then this vanishes, and this one is just trivial. And we get back to our usual part. So now our Lagrangian is invariant under our modular flavor symmetry, which is kind of good. Good. Questions for the general setup? If not, I'm going to show you an example. So actually, just
I have a question.
Yeah, Omar.
Just a quick question. Are these two constraints on the right the ones that determine that you have to use the finite modular groups, or is the other way around? Like you start with the modular groups and these constraints appear.
You start with the modular group, and then those constraints appear.
Okay.
So yeah, you will, for example, see that. So if you consider, of course, string theory, and then take a look at the low energy limit of your theory, you will always see that these orthomorphic factors here will appear in the transformation of the fields.
Mm-hmm.
This already gives you somehow this constraint here. And the new thing, which of course, it is also possible to take a trivial representation here. So for the Yukawa, take a trivial representation here, so that this is really trivial, and you take ky to be 0. Then your Yukawa would really be just a constant number like it was before.
Okay.
This could, of course, also happen even if you somehow have a modular flavor symmetry, but then the point would be lost. Yes, so somehow you impose the modular flavor symmetry and then those constraints pop out. I would say it's this way around.
All right, thank you.
Okay, good. Let's jump to the example. The first example that has been around. So these modular flavor symmetries have been proposed by Ferrulio here in a really nice paper. You should read it. Anyway, his first model, he proposed the following metric content. So first of all, we have a theory which is modular invariant with an gamma 3, which is somehow isomorphic to A4. So we have an A4 modular flavor symmetry in our model. And let's just take the following metric content. So we have the electron muon in town. So we have the three electron generations. We have one is a trivial singlet, a non-trivial singlet, and another non-trivial singlet. Leptons, we say they transform as a triplet under the modular flavor symmetry. And we have a somehow supersymmetric theory. So we have Higgs down and Higgs up. They're both singlets under the flavor symmetry. And we also have this flavon here, which is again a triplet. And from all our constraints, we will see later that the Yukawas also transform like a triplet. And so this is the representation of the flavor symmetry for our metric content. And the second important thing was if we go back, those modular weights over here, we have to specify them. So, okay, there is still 1 degree of freedom. We can take any real, no, not real, any, how do you call them? Not natural, but with a negative sign. Anyway, you take an integer, you take any integer number for x, and you have to take a modular weight of 1. You take 2 minus that integer, 0, minus 3, and 2 as the integer weights. And then you write down your superpotential or Lagrangian. So if you never heard of a superpotential, just, okay, this is really rough, but just consider it to be a Lagrangian. And so we have a superpotential with a so-called Weinberg operator, and this Weinberg operator, this is the letter part here, this will give rise to neutrino masses. So if here there's the usual thing with a Yukawa coupling, which is really a number called alpha, and yeah, the electron, the Higgs, the lepton, and the flavon over here, this will give us usual electron masses, nothing new to that. Interesting here is this Weinberg operator in the rear part, where we have this y here, which is the modular form, the modular Yukawa form. And of course, this full term has to be a trivial singlet. This was the first demand here. And the weights have to add up to 0. So if we take y, y is 2, but you see they have to add. So let's consider y minus 2. So minus 2, 0, 1, 0, 1 is equal to 0. Good. And next thing is we do the A4 tensor products to yield the neutrino mass matrix over here. So we have the y was a triplet. The lepton is a triplet. The second lepton is also a triplet. And the Higgs ups are singlets under the flavor symmetry. Of course, they have... of course, they're not SU2, so they get this VEF and they pick the neutrino out of this lepton. And therefore, we can do this tensor product in the group theory. And we will see that we will get, so the neutrinos in the L's and these Y's from the Y here. And so this will be our neutrino mass matrix. Good. Those Y's are the modular forms. They are a triplet, so they have 1, 2, 3, Y1, Y2, Y3. And of course, they depend on the modulus, which I now named tau. So tau is the modulus. And so what you do is you construct your modular forms of the modular flavor symmetry of A4 or of gamma 3. So you construct the modular forms, not of gamma 3. Yeah, you construct the modular forms of your finite modular group, and you will see that they are quite restricted, and you can write them in an expansion of those Qs. We call them Q expansions. So the Q has the modulus in it. So those are the modular forms, and they transform exactly in that way here with this automorphic factor over here and with the triplet representation over there. So these are our modular forms, and those modular forms are actually the ones that are here sitting in the mass matrix. So the mass matrix is not just numbers, but it depends on the modulus tau. And those are the only dependencies. So your full mass matrix only depends on 2 parameters. And this is really nice, because other way around, you would have numbers that are not constrained in here. And this will give you a lot of parameters in the non-modular way. Good. Coming back, you have a mass matrix with 2 parameters, and now you do your usual stuff. You do a PM&S matrix. You do so you do the masses. You do calculate the mixings. You calculate the UPM&S matrix, and you will therefore get the mixing angles theta. You will get the CP phase, and because we have Majorana neutrinos, we will get those Majorana phases. And of course, you will get the ratio of the neutrino mass differences, so the solar and the atmospheric neutrino mass differences. And you form the ratio between those two such that you don't have to consider the scale over here. So you take your 2 parameters, you calculate your UPM&S matrix and the masses, and you get all of those parameters. So you take 2 parameters and you predict 7 parameters. At least 5 of them you can compare to the experiment. So you do 2 parameters and you compare them to 5, which is really restrictive. And one next thing is you can plot the moduli space. So which moduli are possible and how good do they get to the experiment? And yeah, we have here the upper half plane. So we have the fundamental domain of the modular group. And here in the middle sits the green area. So this would be the best spot to fit experiment. If we take a closer look at this point over here, we get this big picture here. And we see that there are 2 green points. And for you, you said that this big X over here would be the best fit point to fit the experiment. And this is the point that he gave. And what he then did is he didn't only consider the ratio between those 2, but he considered every single one of them such that he can fix the neutrino mass scale. And therefore, he can find predictions for the neutrino masses, which would, in his case, be those 3 masses. And I thought this would be a nice ending, like having the neutrino masses standing like there. Of course, they won't probably be like this, but a roughly idea, or it's a prediction you can do. Okay.
Okay. Thank you, Alex. I don't know if someone wants to ask some more questions, because if not, I am going to ask.
So in that case, I have a question.
I have a question.
Yes.
Okay, Alicia, you first.
Okay,
go ahead.
So from the point of view of someone that doesn't work in this at all, this is more like a technical question. So so first you have your string theory, right? And you have a supersymmetry at the level of the worldsheet to get these 10 dimensions. But then when you're working with compactifications, I think you're working already in the effective field theory, where you are working in the fields in your target space. And here you have also a supersymmetry at the level of these effective fields, right?
Yes, you can. So it depends on the compactification you do. So the compactification really restricts your target space supersymmetry. So you can have, let's say, up to n is equal to 4 target space supersymmetry, which is phenomenology, maybe not that interesting. You can have n is equal to 1, which will give you, or you can even have some MSSM-like, you can even find some MSSM-like particle spectra with an n is equal to 1 supersymmetry. You can also do compactification in such a way that you totally break the target space supersymmetry so that no target space supersymmetry is left. This would in principle also be possible, yes. And the flavor symmetry, also the process for finding the flavor symmetry would be exactly the same, no matter how many target space supersymmetry you've got.
So why do people use the one where you're not, when you have supersymmetry left? It would be the most natural thing to do it with the other one, right?
No supersymmetry. Of course, yeah, it would be. So how should we say? Of course, so this is a really new field. So it's been, so Ferruio's paper has been for 3 years now. So it's really new. People used to do what they have done before and what they know they can do. I think this would be my personal explanation why nobody has looked at it without the supersymmetry by now. But I think it should not be too difficult to go without supersymmetry. I think it should also be possible, like from the bottom up perspective, or from the bottom up way, like without string theory and all. I think it should also be possible, yeah.
Okay, yeah, thanks. I had never understood that part. So
No?
I'm done.
Yeah.
A quick question, Alex, just to know what do the colors represent in this last couple of graphs? I think some kind of deviation from the standard model values. Yeah, okay.
Yeah, this is the usual chi deviation from the standard model. So how should we put it? So you it's calculated like you have for the experiments, you always have a 1 sigma range, and you calculate like how for all of the 5 parameters you compare to the experiments, or 1, 2, 3, 4, 5, yeah. You take a look at how far away you're from the best fit value. You will square it and add them all together, take the square root out of it, and this will then give you your chi, or even chi squared. So what Petkov says, I don't know if it is statistically legit, but what he says, and I don't want to argue with him, is that if you take the square root, so if you take only the chi, this says on how many, so the value that you get out there is a number. Like, for example, here the best fit is, I don't know, 32 or so. If you take the square root of 32, and he would say that this model is a square root of 32 sigmas away from experiment. So Ferruio's model is quite far away from, or not quite far away from experiment. It's quite close. Therefore, that is just a first model that has been proposed, and it's just about. And so his paper was about the concept, and that you can come near to experiment. But of course, yeah, it's not in the 1 sigma range. Of course not.
Nice, thank you.
Okay, but Petkov, for example, has papers which are. Which have a square root of chi of, I don't know, 0.2 or something like that, which are really, really, really close to experiment values.
Yeah.
Yeah.
Thanks.
Alexander, I have a question, a little question.
Yeah.
And you talk about winding numbers and kiki excitations, right?
Yep.
And you use it in the construction of all these things. I'm not an expert here, but what is there exists a quality between these quantum numbers, winding numbers and kicking excitations. This duality is still duality. And my question is, what is the relation of things? There exists a relation here?
You were, so your connection got lost somehow in between. I didn't fully understand what you were saying. I'm sorry. Maybe you can try again.
Let me. Yeah. Let me 1 second. I will move.
Abraham.
I'm back.
Okay.
I'm back.
He's back. He's back.
Could you hear me, Beth? I mean,
I think it's better, yeah.
okay. You talk in the start, maybe in the start of the presentation, in the few minutes. I mean,
Mhm.
and you talk about winding numbers and KK excitations.
Mhm.
And there exists a symmetry between these quantum numbers. This symmetry is T-duality. My question is, there exists a relation between T-duality and your work? Or it could be?
Yes, of course. So so you know T-duality from a circle compactification, right?
Yeah, right. Exactly.
Yeah. And so a circle won't give you a modulus. Maybe I have a nice picture for that. I don't know. So if you only have one circle, like say omega 2, there are not many ways to reparameterize this circle. Actually, there's only one way, and this is the T-duality transformation.
Yeah, right.
So the more general thing, so if you take 2 dimensions, you get a T-duality, but it's more general because you have not 2 dimensions and not 1 dimension, and this would then actually be this modular thing, this modular group.
Okay.
So the T-duality you say is the radius goes to 1 over the radius, maybe you mean like that. And there inside this SL2 set, we also find one transformation that sends us the radius of the torus to 1 over the radius of the torus. So you might say it might not be exactly the same torus. It is still the same torus, but it's just grown bigger.
Yeah,
So
right.
the ratio between the 2 circles stays the same, but it can go bigger and smaller. We would still call it the same. So this T-duality transformation is also present here in the SL2Z. Yeah, also in the modular group.
Yeah, I get it. What in the in the modular framework symmetries, what can we? I mean, no. How can we see the T-duality?
In the modular symmetry itself.
Yeah, right.
Like from a bottom-up perspective.
I mean, it makes sense, this question? Maybe not, I don't know.
I don't know. I haven't thought of it before. This is why I'm struggling. Okay, so to be honest, I have no idea. Should you see this? So
There exists how remanent T-duality in the modular framework symmetry or something like that? Or?
You would, let me put it like this, you would see it like, for example, if you you have here, so you can only, we have this fundamental domain in this upper half plane. So for the modulus, real and imaginary part, we have this fundamental domain. So whenever we're inside this fundamental domain, we have a modular transformation, like for example, the T-duality transformation, that maps us outside of this fundamental domain. And if we then go from this point to, let's say, that point, if we have 2 points and they are connected by the T-duality transformation, they will give us the same observables over here. So this would be somehow the remnant that we see.
Okay.
This does not, since you're already asking, this does not have to be true for, so if you have more elaborate superpotentials, you can have, for example, so here for a 4, you have a triplet times triplet times triplet. They only have one trivial singlet. But if you have other groups, they can also be different, different trivial singlets. You have to add them all together. You get more parameters. And there are parameters that change with when you do a T-duality transformation. They actually change also with this orthomorphy factor. But all the physical observables, they stay the same. So in that sense, you have a lot of parameters that are connected by T-duality, and all the parameters that are connected by T-duality give you the same physics observables. This redundancy is still there. Yeah.
Okay, yeah, right. I get it. So interesting.
This is nice. Yeah, I've never thought of it like this way. This is cool.
Yeah, thank you.
Yeah, thank you.
More questions?
Yes, I'm going to ask a last question about the eclectic group symmetries, Alex. The question is like, how hard it is to find irreducible representations of these groups, in the sense that you have like your fields, and they have to transform under the traditional symmetries, but they transform also under the modular symmetries, right? So you have to have like a compatibility relation. So how restrictive this relation can be?
So what can I say? So they're not okay, so the restriction for the groups themselves is this normal subgroup and the orthomorphisms. We already saw that. And this also is then of course true for the representation, because the representation is always tied to the group. So what you can of course have is, like, for example, in the delta fifth here in the Z3 or before, is that you have a 3-dimensional and a 2 + 1 dimensional case. So this like can happen. You don't only have to have 3-dimensional representations. This is like, there's no restriction in there. But of course, you always want 3-dimensional representation. So I think the representation should, of course, be the same. So if you have a triplet representation, you would also need the full triplet for your full fields. So the fields have to be a triplet under the traditional, and at least a reducible triplet under the other one. I think there are no further restrictions now.
Okay, so it seems like not that hard.
Yeah, I think the most part is for the groups to be subgroup and orthomorphic.
Yeah, that is restrictive enough.
That is really restricted, yeah.
Okay.
Okay, good.
Yeah, that might be my last question, and I don't know if anyone else have some other questions. I think not. No. So thank you very much, Alex, for this nice talk, and thank you everybody for assisting and for being and for having so nice participations today. So thank you very much. Thank you, Alex.
Thank you also.
Bye.